In this last video, instead of giving more definitions, I want to give the motivation of what we want to do next, and actually the motivations for the definitions we will see. In the couple of lectures, we focus on the functions in given algebraic function field f over k. And for each function, we investigate if it has zeros or poles in the set of places. And we have answered this question positively because we can guarantee that there exists at least one zeros and poles for a given function x, for a transcendental x. Moreover, we have also seen that it has finite many zeros and poles, thanks to proposition 113. When we gave an upper bound for the total degree of the zeros of the function x, and in the following lectures, we will also see that the total degree of the zeros and poles will be the same when we count multiplicity. So what I want to mean is that if we include their multiplicities of the zeros and poles, we will get the same integer, same quantity, and we will also see that indeed it gives the extension degree of the function field. Let me illustrate what I want to mean by this equality. For instance, one of the discussion sessions, we have considered the function in the rational function field k of x, which is defined by the fraction of x over x minus a square. Here is non-constant. Here is the non-zero constant. And we have observed that it has zeros at px and p infinity and each of order 1. And it has pole at the place determined by the linear factor x minus a of order 2. And here note that all places, all zeros and poles are the rational. So they are degree 1 places. And the total degree of the zeros, counting their multiplicities, will be the total degree of the poles, including its order. So we get the equality. So, and later we will see that if we define this function as set, k of x has extension degree 2 over k of z. And for instance, again considering the same example, if we suppose that we are in the rational function field, we consider its zeros and poles as a finite set. And later we will see that actually we can write it as a sum of the formal sum of divisors, formal sum of places. But for the moment, we also want to consider the problem for given finite set of places, for instance, only determined by a single place or the finitely many set of places. We will be interested in finding functions which has zeros or poles in this given set of places. And for each finite set, we will observe that these described functions will define a vector space, spatial vector space, which is called Riemann-Roch space. And this will be finite dimensional vector space over the base field K. In order to formalize this the set of finite set of places and the corresponding functions, we will define a spatial group structure inside of the function field, which is called divisors. And each element will be, in some sense, represent the finite set of places. And this spatial vector space structure will be important for us. Let me write it Riemann-Roch space with respect to this finite set A. And particularly it will contain functions prescribed poles and zeros counting their multiplicities. So that means counting their orders, like in this case. For the coding theory point of view, these Riemann-Roch spaces will be a replacement for n plus one-dimensional polynomial spaces. Particularly, to be able to construct some vector spaces over the finite fields, we will be interested of evaluating some functions inside of this space at given distinct places. On the other hand, more importantly, thanks to this vector space structure, we will be able to get an information on the function field, particularly defining what is called a genus. That will be an invariant for the given function field, and it will be a positive integer. And this integer will depend on the dimensions, k dimensions of these L spaces for each divisor. And this integer will give us important information about the structures or the constructions of some function fields, like rational function fields, elliptic function fields, and so on. course, depending on the additional properties. On the other hand, another motivation, particularly for the elliptic function fields, will be to use the group structure of what is called the divisor of a function field. And particularly as we defined as a degree of a place, we will define the degree of a divisor. And depending on these properties, we will be able to define a quotient group, which we will call Jacobian. And in the elliptic curve case, let me denote double star. For the elliptic function field case, we will be able to find a one-to-one correspondence between this group and the set of the rational places. And this bijection will allows us to remove the group structure of the Jacobian to rational points, the rational points of the elliptic curve. And we will be able to conclude elliptic curves also forms an abelian group without using the elliptic curve arithmetic. So in the next video, next week, in order to understand this picture, first we define what we call divisors and divisor group, and correspondingly, we will introduce the Riemann row spaces.